We are in Unit 6. This is Notes 6, Slope Fields. And this is our final notes for this unit, okay? And to introduce this to us, I want us to begin by finding an equation for the slope of a tangent line to a circle centered at the origin with radius 5, okay? So let's start there. Circle centered at the origin of radius 5. What would the equation of a circle centered at the origin with radius 5 be? Well, that would be x squared plus y squared is equal to r squared. If r is 5, then that would be a 25. Okay? So that's the equation for a circle centered at the origin, radius 5. Now, to find the equation for the slope of a tangent line, equation for the slope of a tangent line. It's not we don't want the equation of the tangent line. We just want the equation for the slope of the tangent line. Well, is that not dy dx? So essentially, we're finding dy dx here. Okay? So to find dy dx, I'm going to use implicit differentiation. So I'm going to take both sides of this equation and I'm going to take the derivative with respect to x, right? So we're going to get 2x plus 2y dy dx is equal to 0, implicit differentiation. Now we're going to solve that for dy dx. So I'm subtracting 2x to the other side, and then I'm going to divide by 2y, and I get negative x over y. Question: would this equation, this is a differential equation, isn't it not? Would this differential equation be different if this circle had a different radius? Did that radius of 5 come into play? No, it didn't. So this equation is one solution to this differential equation, but it's not the only solution. Okay? Just one solution. All right. And that leads us to the idea of a slope field. All right? So we're going to make a slope field before we kind of talk about what it really means and entails. All right? On a grid of points, we can draw short line segments through each point with a slope of negative x over y, and this creates what is called a slope field. So let's construct the slope field for this differential equation. Okay? So at the points indicated, I'm going to start at this point right here. So that is the point. That point is 1, 0, right? So the slope at that point will be negative 1 over 0. What is that slope? What does that mean? Well, that's undefined, isn't it? That is undefined. So I'm not going to put anything on that point. Okay? Not going to put anything on that point. Now, realistically speaking, what happens when a slope is undefined? The line is vertical, right? So if anything, I would put a vertical line. But I will tell you that on AP, if the slope is not defined, they don't want you to put anything there. Okay, so I'm not going to put anything there. But you can think of this as a vertical line. So anytime that y is 0, we're going to get an undefined slope. So all of these points that are on the x-axis, I'm not going to put anything there. But remember, we can think of those as being vertical slopes. Okay? Let's go to another point. Let's go to the point 1, 1. At 1, 1, what is dy dx? At 1, 1, the slope is negative 1. So we need to create a little short line segment that has slope negative 1. I like to use a little straight edge for this. You can use your ID tag, you can use a little ruler, any kind of little straight edge will help you. But we want our slope to be -1, which is down 1 over 1, right? So there's my little slope, my little line segment with slope -1. Okay? Let's go to another point. Let's go to the point 2, 1. What is dy dx at 2, 1? Well, that would be -2 over 1, which is -2, right? So over here at 2, 1, I need my line segment to have slope -2, which would be down 2 over 1. So I'm going to kind of eyeball this a little bit. There's my -2 slope. Okay? What about this point up here, 2, 2? What is dy dx there? Well, at 2, 2, we're back at -1. So it's going to line up with the slope that I just made. I like having a clear straight edge to use, so I can see through it and compare. All right. At the point 1, 2, at 1, 2, dy dx will be -1 over 2, so -1/2. So at 1, 2, our slope will be down 1 over 2. So let me get that. There's -1/2, right? What about right here at 0, 1? At 0, 1, the slope will be 0, right? -0 over 1, which is 0. So the slope here is 0. In fact, anytime that x is 0 and y is not 0, the slope will be 0. So I can come and get all my y-axis line segments should have 0 slope. Okay? Now, we would continue and we would go all the way around at all of these points, all right? And if we did that, like the point -1, 1, -1, 1, dy dx would be negative of -1 over 1, so that would just be a 1. We would find that this is also a 1. We would find that this is a 2. We would find that this is a 1/2. Okay? And going around, we would find that this was a -1. This is also a -1. This would be a -2, sorry, -2. This would be a -1/2. Okay? And over here we would have a 1 again, and a 1 out here. Okay? This one would be a 1/2, and then this one would be a 2. Okay? So that's what we would get if we continued finding all those little slopes. All right. This is the slope field. Okay? This gives us the possible, it really does give us the family of solutions. If we knew of an initial point, like if we knew that the radius was 5 here, so that would mean that the point 0, 5 was on the circle. So we could come up here to 0, 5, and we could follow the slope. We could follow the slope of the slope field of each little line segment, and we could draw in our particular solution. What if the slope was 1? I mean, what if the radius was 1? If the radius is 1, then this point has to be on the graph, doesn't it? So we could follow along the slope field and get the particular solution. So this gives us, the slope field gives us kind of the family of solutions. All right? So from here on out, it would be really convenient if you just knew when you see dy dx is negative x over y, think circles. Okay? Think. The y function is a circle. Okay? The solution curve will be a circle. All right. All right. Here are some computer-generated slope fields. All right. So this is the slope field for this function at a lot of points, right? You can imagine how long it would take to do that one, right? But this is the slope field for dy dx is equal to x plus 2, okay? This is the slope field for dy dx is equal to y plus 1. So if we went and did all of our points, this would be our curve. Why is there a horizontal line at y equals negative 1? Well, if you put y is equal to negative 1 in, you get 0, so that each of these slopes is 0, right? Why are there horizontal lines here at x equals negative 2? Well, at x equals negative 2, the slopes will all be 0, right? Let's think about this, too. In this differential equation, all of the slopes only depend on x, not on y's. So at any x value, the slopes are the same. At any x value, the slopes are the same. So if you find the slope at a single x value, you can just keep repeating it for all of those x values. Yeah? For this one only depends on y. Only depends on y. So if you find the slope at a single y value, that must be the slope for all of that y value. All of that y value is the same. Okay? That makes sense? Okay. Okay. We'll leave it at that for right now. And let's see. Oh, let me get my other sheet. Hang on. Okay, here's my other sheet. And let's take a look at this one. Well, this is that negative x over y again. And can you see all the circles? Can you see all of them? In the above slope field, sketch the solution curve going through the point 0, negative 3. Go to the point 0, negative 3, and then to sketch the solution curve, we want to follow the slope at the nearest point. So this, when we go here, I need to have that point. Even if I didn't know this was a circle, and I do know it's a circle, but even if I didn't know it, I'd think, oh, I need to follow these slope fields, the slope. Okay? So I'm following the slope as I go around. Like that, something like that. Okay? Let's take a look at this differential equation. In this one, it does not rely only on x or only on y, kind of like this one. The columns and the rows were not the same, just like this one. Okay? Let's see. in the above slope field, sketch the solution curve going through the point 4, 3. So let's go to the point 4, 3, make a point there. Our first slope is down, isn't it? So if we're sketching, well, I shouldn't say it's down. Our first slope is steep, right? So if we're increasing our x's, we're going to be going up pretty steep, right? Pretty steep. And then as we decrease our x values, it's still pretty steep here, isn't it? But then as I get closer to this, it's not as steep anymore. And then right here, it gets flat. And then what happens? It looks like I have an asymptote there. It gets closer and closer and closer to that line. It may even be on it. I don't know. I'm thinking not. So that would be a sketch of the particular solution that goes through that point. So even though we cannot solve this, this was that one that I said we cannot solve. Even though we cannot solve it, I can see the graph of it. The one that goes through 4, 5, for the point 4, 3. So that's pretty powerful. Even though I don't know the equation of this, but I can see the graph of it. That's what slope fields allows you to do. Even if you cannot solve a differential equation, you can see what the curves look like, okay? Let's do the same thing, but this time we go through -1, -3. So go to the point -1, -3, and now we want to see what that curve looks like. Okay, well again we have a steep negative curve, so it looks like it would go something like, maybe something like this. Again, it looks asymptotic over here, and then as we go down, it just looks like it gets straight. Maybe something like that. Okay, it doesn't have to be perfect, okay guys, but in general you follow the shape. You certainly wouldn't go like that, or something weird like that, because that would not be following the shape of those slopes, those slope field. Okay, so that looks like the solution curve that goes, if this was our initial condition, if that was our initial point. Okay, that solution looks very different from this solution, doesn't it? It sure does. Okay. All right. Then in your notes, I have some tips for reading a slope field. Okay. Look at the slopes along the axes. See what they're doing. Look to see if the slopes only depend on x or only depend on y. We talked about in those first two examples. Okay. Look to see where the slopes are positive and where they are negative. That can help you decipher. Okay. Units on the slope fields may be different. They're not always one, so be careful with that. In this slope field, they have units on the graph, and so they do on this one as well. Did they on our previous sheet? Yeah, they did. But sometimes they don't. Okay. So don't assume it's that like this is the point 1, 1. Okay. All right. Example. Match the slope fields with the following differential equations. Okay. Well, the first thing I'm tempted to do is to one of these is our circle. Which one is our circle? It's this one here. This is our circle, right? So where is our circle slope field? Which one is our circle slope field? It's D. So that needs to be D. These were generated, you guys, on a calculator. These other slope fields were clearly generated on a computer. Okay? Some calculators can generate a slope field. All right. Now for the other two, Well, where should we look? Well, let's see. Here's what I would do. I would probably, you can do these different ways. I like to look at where the slope is 0 or undefined, right? So both of these have an x in the bottom, don't they? This one has a y in the bottom and x on top. So when x equals 0, that's the y-axis. When x equals 0, the slope should be 0. So which of these remaining 3, when x equals 0, the slope is 0. So along the y-axis, the slope is 0. Well, right here, this is where the y-axis, the slopes are 0. Here, the slope is undefined. Here, the slope is undefined. So this one has to be A. Okay? For the remaining 2, I think I'm going to plug in a point. Let's plug in a point 1, 1. Here the slope would be 1. Here the slope would be -1. So of the remaining 2, at 1, 1, which one has a slope that is positive? Well, it has to be B up here, right? These are positive slopes up here. These are negative slopes. So this one has to be B, which means this would have to be C. Okay? So you can always plug in points to find out which is which. Okay? And that's a useful tool. That's a useful thing to do. I like to give it a little analysis first to narrow it down before I get there. But that's fine. Plugging in points always works. Okay. Example 2. Which of the following differential equations has the slope field on the right? Well, I can definitely see a trig function, can't you? Can't you see a trig? I see lots of trig functions. Sines and cosines. But that doesn't help me narrow it down, right? That doesn't help me narrow it down. So let's look at a point. Let's look at a point. So in fact, this at the origin, the slope looks like it's 1. Doesn't that look like a slope of 1 at the origin? So at 0, 0, it would be good to have a slope of 1. So which ones of these have a slope of 1 there? Well, part A, the slope would be sine of 0. What's sine of 0? 0. That's definitely not a 0 slope, so not A. Which means not C either, right? Because at C, the slope would still be 0. So not C. Okay, B. The slope would be cosine of 0 is 1. That works. For part D, the slope would be -1 because of that negative, so not D. So the answer would have to be B. So that's where plugging in a point, a nice point, is helpful. Okay? That's helpful. Another way to do this. Another way to do this problem, because we can, would be to solve that differential equation. If the derivative is cosine x, you guys, what is y? Whose derivative is cosine x? Sine x, right? Do you see that we can draw sine through here? We can draw sine x through here. There's sine x. Plus c though, right? Plus c. That's all these other ones. There's your slope field, right? That's why we have all of these curves and not just a single curve. Okay? So sometimes it's helpful just to go ahead and solve the differential equation. And then you can see the curves in here. But remember, this would be your particular solution or your general solution. Okay? So a few different ways to approach these problems. Okay? Next example. Match the slope fields with their differential equations. Okay? So first I look to see if my circles are there, and it's not there. Okay? So what else can we use? If we were in class, I would give you a few minutes and you would try to figure that out. So you might want to pause this video and try to figure it out yourself and see what you would do. Okay? So here's what I would do on this problem. Let's take a look. I see that this function, this differential equation relies only on x. This relies only on y. These rely on both. So I'd like to go use what I know on this one relies only on x. That means for every x, the slope should be the same. And look, I just went to this one, but I think this one's going to work for me, because look at every x's slope. Here's where x is 5 and all the slopes look alike. Here's where x is 2, all the slopes look alike. Here's where x is 1, all the slopes look alike, and so forth. It would not be like this in this case or either of these two cases. So this has to be B. In this one, this relies only on y. So where y is, now we're looking at y, and all the y slopes would be the same. You see that all these lines are not the same, so definitely not that one. What about all these y's? Well, they're not the same either, so not that one. These y's are not the same. These y's are the same. Where y is the same, all the slopes are the same. Where y is the same, all the slopes are the same. That has to be a D. Okay? Now over here, let's see, what would I do? I would probably do this, and it just varies. Here's what I would do. For this one here, I see that x and y are both squared. So squared. So dy dx is always positive. The slopes are always positive. So here, I want the one with always positive slopes. Which one always has positive slopes? That one. That leaves this to be C, and if I was just looking at this one, I'd say, oh, well, when x is equal to y, the slope will be 0. Where x is equal to y, the slope is 0. And do you see that? Where x is equal to y, the slopes are 0. So lots of ways to do these. And I did this whole thing and never really plugged in a point. And that's always a way you can do it, is plugging in a point. Okay? All right. Number 4. Consider this differential equation. For part A, sketch the slope field on the 9 indicated points. On an AP test, this is how it would be, you guys. At most, they would have you do 12 points. And if it was 12 points, probably 4 or 6 of them would be horizontal. All right? So keep that in mind. Okay. All right, so after that, I'm just going to come in. Let's put in the point 1, 1. At the point 1, 1, and you can do this in your head, at the point 1, 1, the slope will be 2 minus 1, so 1 over 1. So 1. So this slope would be 1. Okay? Then go to another point and keep on going. The point 2, 1. 2, 1 would be 2 minus 1 is 1 over 2 is a half. So up 1 over 2. 3, 1. 2 minus 1 is 1 over 3. Up 1 over 3, or down 1 and to the left 3. Like that. Okay, 1, 2. 1, 2. 2 minus 2 is 0. In fact, anytime that y is 2, we're going to have a slope of 0, right? So I'm going to go grab those. Anytime y is 2, our slope is 0. Okay, 1, 3. 1, 3. 2 minus 3 is negative 1 over 1, so that's negative 1. Okay, 2, 3. 2 minus 3 is negative 1 over 2 is negative 1 half. So negative 1 half. And then 3, 3, negative 1 third. Negative 1 third. Okay? Now, when I'm grading your test and when AP grades your test, they're not going to have a straight edge making sure that it's exactly right. What they're going to do though is they're going to look to see if in relationship this should be flatter than this. This should be flatter than this. And this you can see. You can pretty much see the 1 there, right? And you can definitely see the zeros. These are very easy to grade. Okay. All right, part B. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 3 is 1. Write an equation for the line tangent to the graph of y equals f of x. Add x equals 3, and then use the equation to approximate the value of f at 3.5. Okay, so equation of the line tangent. We have a point. The point is 3, 1. Now we need a slope. The slope will be, we have the equation for slope, so we put 3, 1 in, and we get 2 minus 1 is 1 over 3, so the slope is 1/3. So the equation of the line tangent is y minus 1 is equal to 1/3 x minus 3. And now we want to plug in 3.5 for x. When we plug in 3.5, we get 0.5. So f at 3.5 will be approximately equal to 1 plus 1/3 times 0.5. Okay? That would be a safe stop spot. This is 1 plus half times 1/3 is 1/6, so that would be 7/6. But FRQ, safe stop, absolutely. Okay. Part C, find the particular solution. Find the particular solution to the given differential equation with initial condition f of 3 is 1. Find the particular solution. That's our solving a differential equation, so we need to separate and integrate. Separate and integrate. I'm going to leave the 1 over x here. I'm going to divide both sides by the 2 minus y. And I'm going to multiply both sides by dx. So separate. Now integrate. What's the integral of this? Negative ln absolute value 2 minus y. Why negative? Because the derivative of this is a negative 1, and we need to undo that negative 1. So it's going to be negative 1. okay, is equal to natural log absolute value x, right, plus c. Okay. Oh, look at the y value here. The y value is 1. So this to me is a good time to go plug in our initial condition here. I kind of think I will. I'm not sure though, because I'm still going to have an ln of 3. Well, should we or should we not? Let us, you know what? Well, I'm going to solve. I'm going to do a little work first, because I don't want to get that ln 3 in there. I think I'm gonna, either way. You can do it either way. You'll be fine either way. I don't know. Yeah, I think I will go ahead and plug it in, you guys. First of all, I'm going to multiply both sides by a -1. I'm going to multiply both sides by a -1. Okay. Why didn't the c become negative? Because a negative of c is still c. All right? All right, now I'm going to go ahead and plug in. So at the point 3,1, I have natural log of 1 is equal to negative natural log of 3 plus c. This is 0, so c is natural log of 3, right? So back to my y equation, because I need to put that c value into my last y equation, I have natural log of absolute value 2 minus y is equal to negative natural log absolute value x plus natural log 3, right? Now we have to solve this for y. So e to both sides. E to both sides. And we get 2 minus y is equal to e to the ln 3 times e to the negative ln absolute value x, right? Okay, so e to the ln 3 is just 3. This negative I'm going to pull up to my exponent, and then I have e to the ln 1 over absolute value x. So that's 1 over absolute value x. And now solve for y. Y is 2 minus 3 over absolute value x. Okay, you don't have to do what I did with all that. We could have just solved it right here for y and left it safe stop, and that's fine. Totally safe stop if it's an FRQ. So just solve that for y, and you can leave this mess right here. You could even have left it like this, and that's fine too. Okay? But this is one answer. All right. Time for you guys to go and practice.